Okay, in this presentation we are going to look at independent random variables and cumulative distributions and so on. So this is more abstract and theoretical rather than the applied ones I usually do. So let x and y be two independent random variables and define v as the maximum of the pairwise maximum of x and y and w as the pairwise minimum of x and y. And what we're going to do here is let f of x, now capital F in each case, f of x, f of y, f of v, and f of w denote the cumulative distribution functions of x, y, v the maximum, and w the minimum respectively. And what we have to do here is we've got two little definitions to show that the cumulative distribution of the variable v, f of v t, is equal to the product of f of x and f of y. Okay, the product of the cumulative distributions of x and y. And similarly for the minimum w, show that the f of w t is the cumulative distribution of x plus the cumulative distribution of y minus the product of the two. Okay, and then lastly, one on the exponential distribution. The random variable x has an exponential distribution with a mean of 0.2, and independently y has the same distribution in exponential with a mean of 0.2. Obtain the distribution function of the minimum of x and y and derive its median from first principles. So we'll come back to that later. So the first thing we're going to do here is v, the maximum. Okay, and this is the cumulative distribution here. And essentially, if we were to rewrite that, that means probability of v is less than or equal to t. Okay, that's sort of really, these two sort of statements are equivalent to each other. Now, what is v? V is the maximum of x and y. Okay, so we're saying that the probability of the maximum of x and y is less than t. Now, this is where we require a little bit of lateral thinking. That means that both x and y are less than t. Okay? Less than or equal to t, actually, I should say. The less than or equal to is important, actually, in this case. So essentially what we're able to do is restate this as two independent events, okay, or the two separate events. The probability of x less than t and the probability of y less than t, less than or equal to t, okay? So essentially this is the guile, this is the trick. Being able to restate this statement here as that statement there. And it's completely correct when you think about it, okay? But essentially once we get that, we've really done the job, okay? That's the thing, it's sort of being able to sort of realize that. So essentially what we have here is x and y are independent, so we're able to sort of state this as two independent events. This is the using the independent event rule. Probability of A and B, if they're independent events, is the probability of A times the probability of B, just using first principles. That means probability x less than or equal to t times the probability of y less than or equal to t, which is exactly what we're looking for. The cumulative distributions of x times the cumulative distributions of y. Okay? So something like this actually looks like fairly tough stuff, but actually once you sort of recognize that little trick that we use, it's very easy. And we're going to do the same thing here now with the minimum. And really, we're approaching the question the same way. So f of wt is the cumulative distribution function of w. And that's essentially saying that the probability of w less than or equal to t. Okay? So we have to be a little bit more, it's a little more complicated in this case. Okay? So what that is, that's the complement of the minimum being greater than t. Okay, the minimum of x and y being greater than t. That's complement of that, complement rule. Now, so that is, again, using the same approach that we did the last time, the minimum of x and y being greater than t can be expressed as x greater than t and y greater than t. Okay, so what we have here is 1 minus probability of x greater than t and the probability of y greater than t. And again, as these are independent events, we can re-express this as follows. Okay, probability of x greater than t times the probability of y greater than t. Now, again, what we can do here is express those as the complements, or in terms of their complements, 1 minus probability of x less than or equal to t, 1 minus probability of y less than or equal to t. Okay? So essentially what we want to do, is start bringing f of x into it and f of y into it. Okay? So what we have here is a very complicated looking expression. Okay? But we can rearrange it algebraically very quickly. Okay? So essentially if you work that out, essentially you would get f of x t plus f of y t minus the product of the two. Okay, so it's a little bit more complicated than the last time, so it just requires a little bit of extra lateral thinking, but really it's not so bad. It progresses very quickly once you know, remember this bit here, and then just using the complements. And remember, we want to get things expressed in terms of f of x and f of y at the end, so that's why it was useful to go in this direction here. Okay, it seems a little bit circuitous, but this is the answer that we're asked to get, this one here. Okay, so it makes sense in the long run. Okay, now finally, the random variable x has an exponential distribution with mean of 0.25, and separately and independently y has the same distribution. Okay, so essentially I'm digressing a little bit. X and y should be greater than t greater than 0 there and all that. Okay, so the rate parameter in both cases is 4. Okay, and therefore, well, you can actually t over mu if you want, which is t divided by 0.25, if you're familiar with that. T divided by 0.25, but that will give you 4t as well, just in case you're not familiar with that notation. Anyway, so in brief, there are a couple of things you could sort of clarify there, but in brief, this is what we're given here. Okay, f of x of t, f of y of t both equal to 1 minus e to the minus 4t. So using the formula that we have used above, this is x, f of x, this is f of y, and this is f of x times f of y, which is, because they're the same, really what we get is a squaring there. Okay, so that's why it's squared here. Okay, so this resolves itself quite quickly arithmetically. So the first two terms can be bunched in there, and essentially what we have to do is work this out, factorize this out. Okay, or express it, multiply it out, I should say. Okay, and really stuff starts to cancel out fairly quickly, and what we end up with there is 1 minus e to the minus 8t. So this is the cumulative distribution function of the exponential random variable with parameter lambda equals 8. Okay, so it seems tough, this stuff, but really you can get used to it very quickly. It's just knowing these little tricks is what helps there. Okay, we'll leave it there.